In this video, we're going to discuss graphical summaries of data, and then we'll also get to measuring the center of quantitative data, as well as an introduction to the variability in quantitative data. So recall, descriptive statistics involves summarizing data graphically and numerically, right? And so we're going to start with some graphical displays for both categorical and quantitative data. For categorical data, a popular graphical display is a pie chart. And basically, a pie chart consists of a circle basically that has a slice of pie, hence the name pie chart. So a slice of pie for each category, right? Remember, categorical data are data whose values, for variables whose values fit into one of several categories. And so there's a slice of pie or a slice of the circle that represents each category. The size of the slice corresponds to the percentage in each category. Pie charts are most useful for data that only have a few categories. And so I see an example below. This is a pie chart of shark attacks in the US or by US state. And there are basically, we have Florida, Hawaii, South Carolina, California, North Carolina, Texas, and other states, right? Remember, there's only going to be shark attacks that are responded to by coastal states. And so we see these all are coastal states, and then there's a category for other here. Notice here the biggest slice is Florida, and so that's a visual way to easily see which category has the most frequently occurring, what's the most frequently occurring category versus one of the states with the fewest. And then this, of course, we have this other category that combines some categories together because their slices will be too thin to kind of separate. But that's an example of a graphical display for categorical data. Another way to display categorical data is by using a bar graph. And with a bar graph, it displays a bar for each category. Okay. The height of the bar actually corresponds to the percentage in each category, right? So whereas the size of the slice corresponds to the percentage in each category, for pie charts, for bar graphs, the height of the bar actually represents the percentage or corresponds to the percentage. Remember, we're still talking about categorical data, and it's basically we're going to display the percentages or the proportion in each category, and that's what we have here. Bar graphs are useful when there are several categories and for group comparisons, right? It's a little hard to compare California and South Carolina and North Carolina here when we're dealing with the size of a slice versus looking at basically the height of a bar. It's a lot cleaner. It's easier to make comparisons, right? We can definitely see that Florida is higher just as it was bigger in the pie chart. But then we can sort of look at the height of these bars, which is basically one dimension. In order to height is one dimension, but it is a rectangle, which is two-dimensional. But looking at the height, because the widths of these are all the same. And so looking at one dimension to compare, and instead of looking at a whole area to compare. It's usually better or easier to do with your eyes. So those are graphical displays for categorical data. For quantitative data, we have a dot plot, and basically a dot plot, in the dot plot, each observation is represented by a dot that is placed, that's a D here, that is placed above its value on a number line representing the quantitative variable. This is very useful for smaller data sets. It's good for discrete data, more so than continuous data, although you'll see that this variable here is height, and it is a continuous variable, although we usually notice this height is given in inches, and so we usually report the height in inches discretely, although it is a continuous variable. But as you can see that there is one individual in this data set with a height of 64 inches. There are two individuals in this data set with a height of 70 inches, so on and so forth, right? And so there are times where you will see a legend or what have you corresponding to your dot plot. especially if you have a bigger data set, even though we said that this is good for smaller data sets. But sometimes for bigger data sets, they'll say that, oh, each dot represents 500 individuals or 500 subjects or units of measurement. All right, but that's a dot plot. Horizontal axis has your values of your quantitative variable, and then your vertical axis can have your frequency in that category. The frequency of observations in that data set with that value of the quantitative variable, not category, excuse me. You can also represent quantitative data using a stem and leaf plot. Each observation is represented by a stem and a leaf, right? So these names are self-explanatory. Now, stem and leaf are not as explanatory as, let's say, dot plots, the dot and dot plots. But the stem consists of all digits except the last digit that you're interested in, whereas the leaf is the last digit in numbers, right? Again, this is for numerical or quantitative data. Of course, you're going to have digits, right? And so the stem represents all of the digits except the last digit. Sometimes it's not the very last digit, but it's the digit that you want to reference, the last digit that you're interested in. And the leaf is the last digit. So all digits except the last, and then the leaf is the last digit. Stem and leaf plots are very useful when you want to see all of your actual data values instead of having like the dots over there, right? So for instance, I don't really know what these are. I mean, I can guess that this is 69. In fact, it is 69 for these dots here. But you don't have to do any guessing when you use a stem and leaf plot. And I'll show you with this example here as we construct one. The values below represent the number of calories for a large serving of French fries at fast food restaurants, right? And so there's one restaurant that had a large fry of 260 calories. This restaurant had 280 calories, so on. And the highest one, since these are written in order, has 730 calories, right? And so what we're going to do is we're going to construct a stem and leaf plot for this data set. Now, what I want you to notice here with this data set is that most of the last digits are zero, right? It doesn't occur for 566 and 631, but for all of these other numbers of calories for these large servings of French fries at these fast food restaurants end with a zero, right? And so remember, I said that your leaf is your last digit. It's not necessarily always going to be your last digit. It could be the last digit that you're interested in, right? And so what I'm going to do is I'm going to put a little legend up here, and I'm going to say that my stem is going to represent my hundreds digits, and then my leaf, my last digit, is going to be the digit in the tens place. All right. Now, what we have to do is we have to make a decision on what we do with these last digits here. One way that we can handle this 566 is to keep the digit that we actually see. It's not 570, it's not 560, so we got to figure out what we're going to do with it. Some people say leave this a 6 because it's in the 60s. Some people say use the general conventions of rounding in order to get this digit. And so that's what I'm going to do. I'm going to round this up 566. If I round this 6, I look at this 6 here. Since it's 5 or greater, that makes that 570. And so I'm going to write that as a 570. And then 631, I'm going to say that that's approximately 630 because that rounds down because that is not 5 or more. That 1 is definitely less than 5. So I'll keep that 3 there. And that's what I'm going to use in my stem and leaf plot. And so the way we write stem is do stem and leaves. I'm going to do it vertically, right? All of my hundreds are going to go first. I have numbers in the 200s, 300s, 400s, 500s, 600s, and 700s, right? And so I'm going to put in vertically 2, 3, 4, 5, 6, and 7, right? And then I'm going to do a vertical line. And I'm going to try to draw this straight. And I'm going to put my tens digits that correspond to these numbers here. Well, 260, the 6 is in the tens place. 280, the 8 is in the 10 place. So when I read this stem and leaf plot, this 8 represents the number 280. This 6 represents the number 260. All right, those are my only two numbers in the 200. So I'm going to go to my numbers in the 300. So I go to my stem 3. That's 310. In the tens place is 1. 370, I'm going to put a 7 there. And then I have two 380s, so I'm going to put an 8 and an 8. Those are all of my numbers in the 300s, right? Now I'm going to 400. Well, in the tens place is a 0 for 400. There are two of those. Then I have 430, 450, 480, and 490, right? Then I have 500, 500, 540, 550, 570, which is that 566, another 570, and that's all my numbers in the 500s. And then I have 610, 620, 630, 640. And then last but not least, I have 700 and 730. And so what we get here is we can kind of get the distribution of our data. Remember, the distribution kind of gives you the shape, or it tells you how your data are distributed, right? For instance, there are only two large servings of fries at fast food restaurants that have calories that are in the 200s, right? There's only two in the 700s. The majority are between 400 and 500 in this middle here, with few 200s and few 700s, right? And so this gives us not only a way to actually see the data values, but it also allows us to see the distribution, the shape of the distribution. And so part 8 has asks, how many observations have 500 calories? Well, if we go to our stem and leaf plot, well, we see that there's a 0 there and a 0 there. And so there are two observations with 500 calories. And then how many observations have 500 or more? So all I have to do is count all of these leaves over here. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And this gives us a way to kind of answer those questions really quickly without looking at the totality of each number, right? Now this is helpful because everything is in order here. I even gave this data set in order. If this were not in order, we'd do some ordering to make this stuff make sense. But this is an example of a stem and leaf plot. It's very helpful when you have discrete data or data that you at least round so that you can present it in this manner here. Some other graphs that are used for quantitative data, or another graph, is known as a histogram. Now, a histogram is a graph that uses bars to portray the frequencies or relative frequencies of the possible outcomes for a quantitative variable. All right. Histograms are the main tools used for continuous data. All right. So this is one of the main tools we use for continuous data. I'm not a huge fan of histograms, but that's my personal preference. I really like box and whisker plots, which we'll talk about later. But histograms are a very useful tool. And so in the graph here, we see a histogram. To some, it may look like a bar graph, and there's a big difference between bar graphs, right? So if I scroll back up in my notes to when we had bar graphs, this is an example of a bar graph here. And notice here, there's a space in between each bar, and my horizontal axis has categories, right? That's why we have spaces, because the categories are distinct things. Well, we're dealing with histograms, usually quantitative variables and usually continuous quantitative variables, right? And so there is no space between them because this is supposed to represent a continuum between these things, right? So age as a variable represents the amount of time you've been living. We usually put it in years, but it is a continuous variable. So we don't want spaces because they are possible. Someone can be any value in between these actual values or these numbers that are labeled here. And so here we have an example of a histogram that was taken from our StatCrunch survey where individuals were asked their age. And as you can see in this first histogram here, we have the age on the horizontal axis and my vertical axis has the frequency. And then on the graph below, oh, it's the same shape. Notice here, I'm gonna look at that. Now look at this. They're the same shape, But the difference is, oh, this has the relative frequency. And remember, your relative frequency is your proportion of individuals that are within that specified interval or whatever. All right, and so here we have numbers that are between 0 and 1. It actually doesn't go that far up. 1 is 100%. 0.2 is 20% if you want to think of this as percentages. But here we go. We have our relative frequency here, and then we have our frequency, our count here. And we can see that our axis is definitely counting because we have numbers like 500, 1,000, 1,500, so on and so forth. And so the difference between the two histograms is that the top depicts frequencies, and then the graph on the bottom depicts relative frequencies. So I wanted you to get this example here, because it doesn't matter whether you use the frequency or the relative frequency. If you use all your data or you use the same data, the graphical display of the histogram is going to be exactly the same, whether you use the frequency or the relative frequency. It does not change the shape. Okay. And so what we can do is we can use the frequency graph to get the actual numbers that are in our data set. For instance, it asks about how many people are 19 years old. Well, since I don't know how many people were on the survey, this relative frequency is not going to give me that information if I want to know the actual count. So I have to go to the frequency distribution here, and I can figure that out by going to 19. Now, 19 is basically right in the middle of these two bars here. 19 is directly in the middle of these two bars here. So do I use this bar to represent to help me count the number of people who are 19 years of age, or do I use this box here, this bar here? And the answer to that is that we're going to use this box here. This bar here represents all of the ages from 19 to very close to 20. All right. This bar here, 19, and all the students who had ages from 19 to as close as possible to 20. Notice I didn't use an equality here at 20 because this is not counted in this box here. So the way you read these bars, this is 14 to almost 15. This second bar is from 15 years to almost 16. This third bar is 16 years to almost 17, right? So this is 19 years to almost 20. And so if I want to know the amount, I'll try to go and find the frequency, which looks to be about here, which will approximate that to be 1,400 people. Now, if I want to know the percentage, what I could do is I can instead use the relative frequency, go to the interval between 19 and 20, and this includes 19, and then trace that back to here, and now say that that's approximately 0.16. Well, definitely 0.16 is not a percentage, but we can multiply that by 100, and that'll give us about 16%. Some people may say 17%. We're just looking at this to estimate it. Actually, I'm going to say 17% as well because it actually looks a little bit more than 16%. So I'm going to change that to 17%. But of course, we're estimating. That's why they use the word about. So I'm just going to say 17%. And there we go. All right. So those are some graphical displays. There are more graphical displays, right? I think there's a chart called a Pareto chart, which is like a bar graph, but the categories are in order, either from least to greatest or greatest to least. There are other things that you'll see. Definitely reference your textbook if you see a term or a graph that you're not familiar with, or you can ask a question by sending me an email or asking me in class. Now we're going to talk about shapes of distributions, right? So when we have continuous data or quantitative data, especially like these dot plot, the stem and leaf plot, the histograms, the distributions of the data or the shape of the data may vary, and we want to put some terms on some of those distributions. For instance, a distribution that looks like this is what we call uniform. It's called uniform. In uniform, all the bars are the height of the frequencies or the relative frequencies. It's pretty much the same height across the distribution. Now, it's not going to be exactly the same. Some are going to be lower, some are going to be higher, but generally, the distribution is something like that. That's called a uniform distribution, right? And then other distributions we're going to identify by their peak, the number of peaks they have, right? For instance, these distributions down here, they have a peak here. So this distribution has a peak in this area. This one has a peak in the center, and this one has a peak here. All of them have one peak, and when that is the case, we call that unimodal. All right, and it was related to finding the mode of a data set, but it's called unimodal, and it's because they have one peak. Some distributions have more than one peak, which is this distribution. It has two peaks. So instead of saying unimodal, we're going to say bimodal. Bimodal. Now, let's go back to this unimodal distributions. All right. I said that they have one peak, which we've identified the peak, and they also have what we call a tail, right? This peak is on this side, and on the left side of the graph, it has a tail, what we call a tail, right? So it has one peak and one tail. This one has a tail that's on this side over here. This is the tail. And this one has two tails. It has a tail on this side, and this one has a tail on this side, right? So this part of our distribution is the tail, right? Well, when the tail is on the left, we call this skewed to the left. When the tail is on the right, we call it not right. I guess you could call it right-tailed, but we call it skewed to the right. And this one has two tails, and they're on the end, and the peak is in the middle. So we call this, it has two tailed, but it's symmetric. It's neither skewed to the left or skewed to the right. We don't call it symmetric. It is symmetric. That's a synonym or a description for it. But we call this one bell-shaped. And so we can have a unimodal distribution that's skewed to the left, skewed to the right, or symmetric or bell-shaped. All right. And these are some terms that we'll get used to when we're describing quantitative graphs of quantitative data. Okay. What we're going to do is we're going to switch gears here. We're going to get to some other statistics, which is numerical summaries, right? And one numerical summary that we're going to look at, or multiple numerical summaries, have to do with what we call measures of center. All right. A measure of center is a typical value of your observations, right? One of the most widely used measures of center is your mean or your arithmetic average. It's the sum of all observations for a variable divided by total number of observations. By the way, when we use the variable x in statistic, it means your observations. It's the value of a variable for a person in your data set, right? And so let's review some of the symbols that are related to your mean. For instance, your population mean, there's a symbol that we use, and then you have your sample mean, there's a symbol that we use. The symbol for your population mean is the Greek letter mu. I spell it out here. And the symbol for your sample mean is X with a bar, all right? And basically the formula for that, X bar, your sample mean, is we use a sum. This is your Greek capital S or sigma, all right? we add up all of our observations. Again, I said the X represents your observations, right? So we sum up all the values in your data set for that variable, and we divide it by the number of observations we had. N is the number of observations. And some people call it your sample size. All right. So we do sum up all your observations and divide it by the number of observations you have, which is N, and that is your sample mean. The median, there is no formula for this, and there's no symbol for this, but it is the midpoint of the observations when they are ordered from least to greatest or greatest to least. And what you have to do is you basically have to count off until you get to the middle number. Now, if there are an even number of observations in your data set, then the median is actually the mean of your middle two values in your data set. All right, so that's your median. And then last but not least, we have the mode. All right, and I didn't have this up here. But your mode is the value or your values that occur most frequently in the data set. So it's the number that appears most often. And if there's no number that repeats itself in your data set, then you don't have a mode. You'll always have a mean and a median. You may not have a mode. All right. And so let's look at this example here where we calculate the mean and the median of a data set, right? So it says the values below represent the CO2 pollution of the 8 largest nations, right? So 0.2, 0.7, so on and so forth, 9.7. Let's calculate the sample mean, right? I'm going to do the sample mean, which is given by X bar. That's sum of all of your observations divided by the number of observations, right? So I'm going to do 0.2 plus 0.7. That's my second observation. My third X or my third observation is 1.1. My fourth X or observation is 1.2. My fourth one is 1.8. And we get 2.3, 9.8, 19.7. All right, that's 8 observations. Of course, they told me that too. I had to count. And so that is 36.8 divided by 8, which is 4.6. So this is saying that a typical observation is about 4.6. Now, when we do this, this is like balance. The mean is like balancing a weight and finding that center. Like, so if we put our values in order and we wanted to, let's say we had like I don't know, a scale. It's not a scale, but one single point and a board, and we wanted to balance that, then the mean will be where we would have to put it in order to balance that data. So my mean is going to be is 4.6. So if I had a number line, I put it on 4.6 and I held that up, and it would balance my data set. So it's like a balance point of your data set. That's one way that you can interpret it. Your median, some people use a capital M, but we're just going to spell out the word median for now. When we get to quartiles, we'll call it something different. But our median is just the midpoint or the middle number. It divides your data set into 2 equal parts. And so notice here we have 8 numbers. They're all in order. So when we have an even number of data points, then the middle 2 numbers, we have to find the midpoint of those, which is the same thing as the average. So it's going to be 1.2 plus 1.8 divided by 2, which is 1.5. Okay? And so this divides the data set in half. And so what we can say is that we have half of our observations are below 1.5 and half of our observations are above 1.5. That's an interpretation of the median. Let's go to part B here. It says the dot plot below is the dot plot for the data set. Are there any extreme values in the data set? If so, remove the extreme value and recalculate the mean and the median. So what I'm going to do here is I have my dot plot. This is that 0 0.2, 0 0.7. Notice here, my dot plot put the 1.1 and 1.2 on top of each other. All right, because they're so close to each other and it needed space, right? There's not enough space to put them side by side. So the computer software automatically did that. That is okay. Sometimes your computer software is going to do that. Then we have that 1.8, that 2.3. Then we get to these values here and here. Now, this one is definitely extreme. Extreme means very different from the other values, right? This one is definitely DEF or definitely extreme. This is potentially extreme. We're only going to focus on one of these. And so what I'm going to do is I'm going to look at this value here and I'm going to take that out. That's that 19.7. And what I'm going to do is I'm going to recalculate my mean, right? So remember, that's the sum of your observations divided by n. If I take out that 19.7, well, the sum on the numerator with 19.7 was 36.8. Well, if I subtract 19.7 from that, I'm going to get 17.1. And since I removed that 19.7, I now have just 7 values in my data set. And this will give me 2.44, so on and so forth. Now my median, after I remove that, well, now I have just 7 data values, right? So 1, 2, 3, 1, 2, 3. This is my new median, which is 1.2. So with the extreme values in my data set, I had a mean of 4.6 and a median of 1.5. And now my mean has dropped tremendously down to 2.44. And then my median is 1.2. And so what has happened? It says when the extreme value removed, what happened to the mean and the median? I'm going to type this. What happened was that the mean changed substantially. The median only changed slightly. Okay. And basically what this means is that the mean is highly sensitive to extreme values, right? It went from 4 point something to 2.4, 2 point something, right? That means it's highly impacted by or sensitive to your extreme values if your data set has extreme values. I don't like that little piece there. But your median went from 1.5 to 1.2. It only changed slightly. So the median is resistant to extreme values. It's not influenced by those extreme values. And so on the top of the next page, these are the effects of extreme observations. Another word for extreme observations are outliers, although there's a different definition or a way for you to find those values besides just looking at a dot plot. But the median is not sensitive to outliers or extreme values, while the mean is sensitive to those extreme outlying observations. All right. In fact, the mean, all right, I'm going to do this. Let's see if you can figure this out, right? Notice here, most of my observations are here on this side of my dot plot, right? Versus there's a single value here and a single value here. So if I were to do a histogram or a distribution, my distribution is going to look like this. Uh-oh. It's going to look something like that. Creating a graph that's skewed to the right, okay? Now, if I remove that, well, it's skewed to the right. Now, the median of this distribution was 1.5, right? Which is somewhere in this area here, 1.5. That's the median. while the mean was 4 point something, which is here. Notice that the mean is closer to the tail of that distribution um, compared to that mean. Or it's on this side of the mean is on the right side of the median, which is closer, which is the same side as the tail of that distribution. All right. The effect that the mean that the extreme values have on the mean is that it's going to pull the mean closer to the tail of the distribution compared to its or relative to its location to the median. Okay. And so if I have a distribution that looks like this, the extreme values are always going to occur on the tails of that distribution, right? This distribution here is skewed to the left, right? And so what's going to happen here is that my mean is going to be less than my median because my mean or my extreme values always pull my mean towards that. And so my mean is going to be somewhere over here. And so in this distribution, my mean is going to be less than my median. Okay. In the second distribution here, we have our extreme values here and our median here. Remember, the extreme values push your mean towards the tail, so your mean is going to be somewhere here on your distribution. And if it's to the right, that means your mean is greater than your median. All right, in this case, our graph is skewed to the right. The tail is on the right. And so when my graph is skewed to my distribution is skewed to the right, my mean is greater than my median. And then the last case with these unimodal distributions, we have a two-tailed distribution that is symmetric. There's our bell-shaped distribution, which is one of the most popular and well-known distributions in statistics. In this case, our mean equals our median. The mean equals the median. All right, and that's going to be all for this video. We'll see you in class.